Hello guys, it's Ert here, and this is the 8th and final episode of Rewriting Physics. And today is just a summary of what we've covered and an explanation of where this notation came from. So first, let's start talking about where the notation came from. And so as a college student going through physics class, I was starting to get confused by all the V's and A's and all of those other letters. So we had at least 3 different uses for V: voltage, velocity, and volume. And then we had 2 uses for A: acceleration and area. And of course, lowercase a could be either. And overall, the physics notation in that class was just messy. And of course, you also had resistance, which could have also been a big R radius. Yeah, things got a little messy there. So I decided, let's take the mess out of the notation and just start completely over. So with that being said, the structure of this notation, after a pretty long time, is you have 2 different unit assignments per letter. The first is just the regular letter. The second is the tilde variant, and I'm using F as an example. But each of these objects is called a subconcept. And of course, you vary this by an nth power and a unit. And from now on in this episode, epsilon has units of capital epsilon. This capital epsilon isn't an SI unit itself. Instead, it is a replacement for whatever you set epsilon to be. For example, if you set it to be charge, it will be coulombs. If you set lowercase epsilon to be length, you'll have units of meters. So, with that being said, FU to the N has units of kilograms times the SI unit per second squared times meters per the SI unit to the N. And this F tilde has units of 1 over seconds times meters per the unit to the N. And of course, there's more to this notation, but that is the basis of this. So let us start with FQ squared. This is voltage, and so this will just have units of kilograms times coulombs per second squared times meters per coulomb squared. And of course, you can do frequency with coulombs as well, but I haven't seen a use for that yet. And now I will show all of the letters, all of the subconcepts on screen right now, with all of their SI units listed out and their names, or what they're based off of. 2 specific ones that I want to show that are unitless on the photos are rho and, well, the var rho variant, and W. These are all unitless, and rho is just a ratio. So let's say you are going for x epsilon, of which we will cover why this notation works later, but rho is just a ratio, so you have x epsilon over x prime epsilon, and then if you want to subtract something from it, let's say you want this ratio, so like this, all you have to do is put a minus sign up there. And then rho tilde, or var rho, whichever way you want to write it, is x epsilon minus x prime epsilon over x epsilon plus x prime epsilon. So there's that. These are just simple ratios. These will always be unitless. And then weight. Weight is a special one used for averages. And of course, this could also be a percent, but this is just using averages. So now I would like to look at the diacritics that you use on top of these letters and the one diacritic you use under them. So the diacritics you use above and below these letters consist of the macron, the breve, the inverted breve, and the ring in vertical order. So the macron just flips units over. So for example, with force, what we just had was kilograms times the unit per second squared times meters per the unit to the N. All this does is just flips it over, and thus F bar has units of kilograms times a unit under second squared times meters under the unit to the n. And then you also have the breve. And all the breve does is take the main unit and change its exponent to -2 minus the original exponent. So how this looks with, again, force is we already have the original, and this exponent is going to be a 1. So the new units are kilograms per second squared, and then this exponent will be -2 minus 1, or -3, so we put it on the bottom, times meters per the unit to the n. And then you have the inverted breve, of which just inverts seconds, inverts the seconds exponent. So for the new force, this would have a breve on it. For the new force, this would be kilograms times the unit times second squared times meters per the unit to the n. And then the ring just combines both of these operations together. So for the ring, you have kilograms times second squared per the unit cubed from this effect and this effect times meters per unit to the n. Now, there is one last diacritic called the cedilla. All this does is lets you know that the letter that the cedilla is on is a constant. So for example, the way you tell this, the way you tell resistance apart from the ideal gas constant is you just put a cedilla on it, like this. That is very fat, but you get what I mean. And similar thing with Avogadro's number. In this notation, it's just in with a cedilla. I don't know why that's drawing that fat. The next thing I would like to look at are the diacritics for densities. And the main part of this notation, instead of using rho for volumetric density, or sigma for surface, or lambda for linear, we are using diacritics to express those. So I will write down the diacritics one by one. And we start with x over length. You'll notice this looks kind of like an L, and x times length. And you'll notice that when we go from division to multiplication, the diacritic here just flips over. That is not accidental. So with that being said, we have x with this diacritic, that is x over area, and we have x with the reverse, which is x times area. And then we have x over volume, which is this, and x times volume, which is this. And then you also have angle diacritics. So x over an angle is this, x times an angle is this, x over a solid angle, so that has units of radians squared, would be this, and x times a solid angle is the opposite, so this. And then you might have multiple of these diacritics on one letter. So what you want to do is you just want to combine them in a slightly different way. Instead of just doing something like this, because this could get very tedious and annoying, and it just starts to look messy, you combine the diacritics with a few certain rules, and I will put these rules on screen now. The first rule is that when looking at the length or area diacritics and combining them with volume, you combine them such that one leg of the diacritic is overlapping one leg of the volume diacritic. When overlapping, you can do this, 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 or this with volume, and of course, a similar thing applies with not that way, but with the multiplication diacritic. But the only other rule is when overlapping radian diacritics. If you're overlapping angle diacritics onto a volume diacritic, you overlap the vertical part of the angle with the vertical part of the volume. So it would basically end up looking like that. Really, it'd be like that. And then if you don't have a volume diacritic, let's say you have this, for example, this would be over length times area from this. you overlap the radian diacritic with the rightmost vertical line on the length or area diacritic. So those are the rules there. And then when combining these with tildes and rings, you just do this kind of thing. So I will actually show an example of that. So with force, you may have a macron and then you put a tilde over it, and then you can do a ring and this, for example. If you only have the ring, then it's just this. There could also be a macron, but you know, that's the messiest that this notation will get, other than the subscripts, which we will cover next. And now I would like to mention how you get these diacritics. I have created my own package with all of these features included in it. And one of the commands in this package is the DC command in LaTeX. And what this does is it draws the diacritic for you. You can also use /ch if you want the raw character for it. But when you want to type a diacritic onto a character in LaTeX, all you do is concatenate this with the letters that you need to choose this diacritic for. So we have capital L for multiplying by length, lowercase l for dividing by length, and then area, capital A for multiplying by area, lowercase a for dividing by area. And similarly, you have V for volume, N for degrees, O for solid angles. And then you can also combine this with the tilde for T, with the U for the breve, the S for the inverted breve, or R for the ring. And then finally you do I for the macron, and this is in this order. If you aren't multiplying or dividing by a specific thing, say area, you just leave it out. So for example, let us look at force. Let's try to divide by volume. Let's say multiply by area and divide by theta. And what this diacritic would look like, we have started by dividing by volume. This is the most important step. Dividing by theta looks like this, so we join it with the volume diacritic. And multiplying by area looks like this, so we also combine that with the volume diacritic. That's how it looks. The command, again, we go in order from length, area, volume, degrees, solid angles, and so on. So let's actually make this frequency so we can put the tilde above it. And we get /DC times area, so uppercase A, divided by volume, so lowercase v, and divided by an angle, so lowercase n. And then we're adding a tilde on, so lowercase t. And of course, if you just want the raw character for this, you can always just do ch, capital A, lower v, lower n, lower t. And then if we want to do a breve, let's say we were flipping those units over, or an inverted breve in this case, that would go on the left here. Let me redraw that real quick. With that being said, that's how you get these diacritics. And the last thing is if you want to invert it, so add a bar on it, you just add an I and then an I. That's how easy it is to do these diacritics. And then you just bracket it with whatever you're putting the diacritics on, in this case F. Editor here, I just need to make a correction. This diacritic here is actually times theta. So what you'd actually get here is, if I'd done the formula correctly, we would have gotten that. We would have gotten this over volume, and this n would be capital. So there you go. This n would be capital 2. And if we had gone with the correct diacritic, that is FA over theta V, we would have actually gotten this diacritic, and thus the diacritic here would have been, we're going over volume, then times area, and times volume. And of course, again, we just have the lowercase n here. So with that being said, Let us move on to the next part of the video, and that is the summing subscript. What the summing subscript does, well, exactly as it sounds, it is a subscript to sum things. Let us say you're summing together a bunch of voltages, which would in traditional notation be V, but in our case it is FQ squared. If you're summing them together, you would add a plus sign. There's an option to use the power of n and what you're summing over. So that is just a sum over k of the concept. In this case, it's FQ squared with the index of k, which I will denote like this. And then you put this to the power of n, and you root it also to n. So that is what that equals. And of course, if you have a 1 as an n, you don't really have to put any of that, but that's how that works. And let's say you want to average this or put a weight on it. In that case, you add a bar under the plus sign, or in other words, turning it into a plus minus sign. That is easily just /PM in LaTeX. And with that, that just adds a weight to it like this. Now, there's also one other thing I would like to do, and that is I would like to cover what happens if we want to flip this n over. So in that case, we will look at resistance, Q squared. In this case, the n will just be a 1. Well, it will be a -1, but I will write this in this way anyways. This is the nth root of 1 over sum over k. Let's go for -n here, of f to the -n. Actually, it's r to the -n, I'm sorry. R to the -n, Q squared, keeping k constant. And of course, you can always weigh it like this. And so when putting a negative exponent inside of a subscript, things can get pretty messy. So I have included another symbol in the package, which looks like this. And it is just /mpm. Of course, if you're not weighing something, you can always do /mp, which is just a regular LaTeX command, and that will remove the weight here. And so the next part I would like to look at is coincidences in notation. So I would like to look at Avogadro's number, of which is technically a constant, so it would be written like this in this notation. But n also looks like the capital version of nu, which is frequency in this notation. In fact, if we went for mu eta, it would be 1 over moles, which is the exact units that Avogadro's number has. So realistically, you could denote it like this and be perfectly fine. Or you can technically just not include this adilla and be fine. Next one is molar mass, and molar mass has units of kilograms per mole, and it is denoted as mu eta. But of course, the capital version of mu is just m. So no matter what, that notation stays the same. And I will say I have designed this notation to be compatible with current physics. So there are a lot of symbols such as E, F, R, and B, and mu that when put with certain objects just keep the same notation because they are designed that way to do so. For example, E of length just has units of energy. Force of length is just force. Resistance of Q squared is resistance. B of Q is the magnetic field. And mu of, I believe, -1Q is the permeance. And I would also like to mention a quick thing with subscripts. The default power in a subscript of a unit is 0. So anytime you see an object in a subscript without a power, just assume it to be 0, unless it's a sum, of which you'd assume it to be 1. And then the last thing I would like to cover is just some other accessory commands that are in the package that I've created that I will link in the description. Firstly, I have /UNS of a letter. We will go for X. And all that does is just does epsilon to the n. And there's also some other accessory commands that I have that can be accessed within the package, which again, I will put in the description. However, I would like to mention that this uses ticks and upright Greek. There's that, and it also uses the package LaTeX, which is how I get all these custom characters by drawing them. Hopefully through this video you've seen just how this notation works and how it can be used. You can go a lot deeper into this and do a bunch of other things with it, but you can also look through all the other videos I've done on this series and also look at other different concepts. If there are any physical concepts that this notation does not cover, just please notify me and I will work on finding a representation for it. Although I should mention there are still a lot of letters that haven't been used and a lot of tilde variation letters that have not been used either. So with that being said, I will show the free letters on screen right now. And they're the ones that you can use to define a new concept without conflicting with any other letters in this notation. And of course, there are other objects such as you might want to look at pressure or work or things like that that just have their own letters. So with superscripts, you might sometimes have two different objects with the same exact units. Let's say you have, that is a really fat F. Let's say you have a voltage that comes from a capacitor and a voltage that comes from a resistor. You can use superscripts to represent where they come from. And really, capacitance would just be this. So you can use superscripts to describe exactly where the concepts came from. And you can also use subscripts to say something like out or in. So with that being said, thank you so much for watching this video and this series, and I will see you next time. Bye bye everyone, and peace.